So welcome all to week 11 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR IIT Bombay. The topics that I intend to cover today is like examples of discrete and continuous random variable. We saw what are discrete and continuous random variable in the last class, but today we'll look at some specific types of distributions that are useful. Okay. So also we'll look at something related to joint distributions. One thing that I mentioned in the last class also, so there is a book by Sheldon Ambrose, which is titled, I can tell you the title. So this is Introductory Probability and Statistics for Scientists and Engineers, I guess. Introduction to Probability and Statistics for Engineers and Scientists. So this is a pretty good book to solve a lot of examples and to clarify your topics. So if somebody is interested, he or she can refer to that book. Okay. So I'll begin with the simplest discrete random variable, which is known as Bernoulli's trial. Okay. So what is a Bernoulli's trial? So Bernoulli's trial is applicable whenever you have two possible outcomes for any event. For example, if you toss a coin, it can have two outcomes. Either it can be head or it can be tail. Or for example, if you talk about event of raining on a particular day, so either it can rain or it cannot rain, right? So another example can be if you are playing a game, either you can win that game or you can lose that game. Like if we ignore the possibility of drawing the game. Okay. So if you have an event which have two outcomes, so you can map one of the event to win or won, okay, and map another event to 0. So for example, you say that if you get head, you map it to 1, okay, and if you get a tail, you map it to 0. So if you want to work with this kind of random variable and you have tossed your coin only once, so one toss of a coin is known as Bernoulli's trial, okay, where P denotes the probability of success. So probability of success means probability of 1 occurring. So in this example, if you assign head to be 1, so probability of 1 means probability of head occurring. Okay. So what is probability of tail? Then it would be 1 minus P. Okay. So you can easily calculate its expectation. So the random variable here takes only two values, that is 0 and 1. 0 with probability 1 minus P and 1 with probability P. Okay. So what is expectation? Expectation of X is 0 into 1 minus P plus 1 into P, which is P. Okay. So to remember, you remember Bernoulli's trial as like you have tossed a coin. If it lands head, this is 1. If it lands tail, that is 0. Okay. So this kind of a trial is known as Bernoulli's trial, where you have two outcomes. Okay. But in practice, it is possible that you toss a coin, let's say 10 times, and you want to see like how many times you got head. Okay. Or you want to find the probability of event that you got head 5 times out of 10 times. Okay. So that kind of phenomena is covered by something called binomial distribution. Okay, in binomial distribution, you repeat independent Bernoulli trials. Okay, so you toss a coin first time, okay, then independently you toss another coin, and these coins are identical also. It's not that for the first time you will toss two-headed coin, and for the second time you are tossing a coin which has both the faces as tail. So the coin should be same for your complete experiment. Okay. So this is a independent plus identical multiple Bernoulli trials. Okay. So let's take a very simple example before we look at what is probability mass function. Let's say you toss a coin 10 times. Okay. And so like, and you have to find what is the probability of getting 4 heads. Okay. And let's say the probability of getting a head on a single Bernoulli trial is given by small p. Okay. So you toss 10 times and you want 4 to occur at head to occur at 4 positions. Okay. So you have 10 places to fill and you have 4 choices to 4 places to fill among these 10 empty places, and rest of them can be your tail. Okay. So you are getting head 4 times, that's why we raise p to the power 4, and you are getting tail for rest of the 6 times, that's why we raise 1 minus p to the power 6. Okay. So this is how the formula for Bernoulli trial is motivated. So if you have, let's say, n independent and identical Bernoulli trials, then probability that you will get x is equal to 1 I times is given by NCI, that is you are choosing I positions from n positions, p to the power I because I times your event has occurred, and 1 minus p to the power n minus I because your event has not occurred for n minus I times. Okay. So this is your probability mass function for binomial distribution. Any doubt till this point? Then we'll move to an example on Bernoulli, this binomial distribution. Any doubt on this? Okay. So I'll move forward. Okay. So the question says, it is known that a disk produced by a certain company will be effective with probability 0.01. Okay. So let's say if for a Bernoulli trial, your event of success, that is 1, is that your disk is defective. Okay. Then the p parameter that you have is 0.01. Okay. And independent of each other, that is the condition for Bernoulli trial becoming your binomial distribution. The company sells the disk in packages of 10 and offers a money back guarantee that at most one of the 10 disks is defective. So if in a pack of 10 at least one of them is defective, then it gives you the company gives you a money back guarantee. Okay. So the first question is, what proportion of packages are returned? Okay. So actually you want to find the probability that your package is returned. Okay. So let X denote the number of defective disk in pack of 10. This should be okay. So if your X denotes the number of defective disk in pack of 10, then what is the package is returned? That you have less than so the company offers you a money back guarantee that at most one of the disk is defective. Okay, it should be at least, I guess. Just give me a second. Just give me a second. Yeah, the question should be that, like, if at least one of them is defective, then you should get the money back. Like, it does not make sense that if at most one of them is defective, then you should get the money back. So if one or more than one is defective, right, then you should get the money back. Yeah. Okay.
Excuse me, sir.
Yes.
It may mean they should have zero defective. If any defective is there, they will return.
That's what it should mean. But the line
Yes, sir.
says that money back guaranteed that at most one of
But
such,
at least there is one.
it should be at least one, right? So let's say if two disk is defective, then according to this line, you should not get a money back. But intuitively, you should get a money back when your two disk is defective, right? Okay, so we will go by the intuition that if one or more than one disk is defective, then you should get a money back. Okay. So how is that calculated? So probability x is greater than equal to 1. That is the number of defective disk if it is greater than equal to 1. Then this is what you have to calculate. What is this equal to? This is equal to 1 minus probability that your x is equal to 0. Okay. So how do we calculate this? This is your 1 minus. Now there are 10 disks in the packages. So 10C0. Your P is 0.01 to the power 0, right? And this is 0.99 to the power 10, right? What is this value approximately equal to? This first one is 0, sorry, 1. So this is 1 into, this would also be 1. And this would be 0.99 to the power 5. Okay, so this is what we have to calculate. You can just have a look what this value is. So this is 99 to the power 5. This is 0.951 approximately. So this is 1 minus 5, 1. So this is 0.049, right? So this is how we can go about a binomial distribution. Okay. Let's look at the second question. This is sort of a bit more interesting. Okay. So give this question a minute and read, then I'll start solving this.
Can you please show the above question again?
Okay. Yeah. Can I move?
Sir, In this question, it is asking about if someone buys three packages, then what is the probability exactly one of them will be returned?
Okay, so that also you can solve. So now you have calculated the probability of, so this should be one more zero here. So this is 0.049 approximately. So now you have calculated the probability that what is the probability of one package being returned. Okay. So now let's say he says that somebody is buying three. So this is your now new P1. So you can calculate that value by, so out of three, you want one to be returned, right? This is the question, right? That exactly one of them will be returned. So this is 3C1, P1 to the power 1, and 1 minus P1 to the power 2, right? You can just calculate this putting this value of P1 over here. Okay. So there were a lot of decimal calculation, that's why I sort of skipped. But the concept remains exactly the same.
Sir, in the above calculation,
What, sir?
1 minus of 1 into 1 into 0.99 power,
5. It
then it
should
should
be
be 10, I think.
10, right? Yeah.
Thank
And
you.
then the value would change. Yes.
Yes, sir. Yes, sir.
So then it would become 0.9043.
Sir, can you show once again the question, sir? I think we can reframe the question. Can you show the question once again, sir?
Sure.
Just a minute, sir. I'll read. Sir, is it like that? The Bernoullis will apply in the last stage where they asked if the three packages I am buying,
Yes.
what is the probability of one I will return it.
Return. Yeah.
So that is basically probability of one is defective. That means one package is defective. The definite
Yeah.
defect is different.
Yes.
Let us see in that way what is the probability of one pack is defective
Yes.
out of three. So three combination and one whatever last part. Okay.
Yes.
Before that part, how to define the one packet is defective? That's the question. Before doing that second part, correct?
Yeah.
So
So,
how to define a packet is defective? They're telling the probability of there is a packet is 10 disk.
mm-hmm.
In that probability of any see what they already they told clearly, if any one disk is defective, it will be defective pack because they
Yes.
don't allow one also defective.
Mm-hmm.
Okay.
Yes.
So then question is what is the probability of one or more defective in the pack? Once you find it, then you can apply Bernoullis.
Yes.
Am I right, sir?
So that's what we did. So here we calculated that what is the probability that one or more than one is defective.
Okay.
Okay. So
But
that is,
but, but that's,
yeah.
that's what the small doubt. Um, yeah, that finding the one or more defective in the pack, there is a required to apply Bernoullis, or it can be directly calculated the independent that the one disk is 0.001 something was there. So when it's
Uh,
independent, you multiply that 10 time multiplication. Am I right? Independent
uh,
disk,
yes,
independent
actually.
event.
So one disk is independent, but again you need to choose where that particular thing is defective, right? So that
No.
that will lead you to 10 1, right?
Mm-hmm.
And then you can multiply different positions, right? So
Yeah.
also here you have to calculate that one or more than one is defective, right?
Yeah, the question is actually any disk is defective is
Hmm.
independent. It is doesn't relate to any pack. How it is
Yes, yes,
which pack was. It's independent actually. Okay,
yes.
so it is actually if I take the 10 disks, what is the
Hmm.
probability is defective?
that one of them is defective.
One or more. At least one is one or more actually. So what then that means you can put ulta reverse way. What the probability is zero defective.
Zero is defective, right?
Yeah, yeah. Then that will be required
That's
to do
essentially same
the.
is what you are saying, that every position is working. So that's what you
Mhm.
got, 0.99 to the power 10. So that's
Yeah,
actually
yeah.
what you got. The other way
Yeah,
around.
yeah. So this is nothing but 0.9 multiplication by 10 times. There's nothing but same only. Independent event. It is the same equation of what we done in the independent event means multiplication of all the. Am I right?
Multiplication. Yes.
Yeah.
But when you
Okay.
have like, if you had like probability of x is equal to 5,
Mm-hmm.
then also you can see that you have to choose like 5 uh, position out of 10 places, and at those
Mm-hmm.
5 places you are multiplying again independent same. So p to the power 5 means that you have the event has occurred 5 times. That's why you multiply p 5 times. And p has not occurred 5 times. That's why you multiplied 1 minus p 5 times. So that's how we reach to this Bernoulli distribution formula. Eventually, what you are saying is actually already captured in this Bernoulli distribution formula. That's how
That's
people have derived it.
that's how this that's how this formula is derived.
Yeah. Okay. So let's look at this question. Just give it a minute and just read this question. Okay, so I think I don't remember the who gave this theory, this dominant theory, but like when genes sort of occur in pair, so let's say here they have given example of blue and brown eyes. So let's denote blue by X, and okay, so because both of them are blue, I'm not using BB. So let's denote blue by X and brown by Y. Okay. So if a person has, let's say, XX gene in him, right, then he will have blue eyes, right? So he'll get one gene from his father, one gene from his mother, and he will have blue eyes. Okay. If that person has YY, again this is simple, that he will have brown eyes. Now among the genes, one of them is a dominant gene. Okay. So here they have given that brown eyes is a dominant gene. So if somebody has XY or YX, so even if this X is present over here, you won't have blue eyes, but the person will have brown eyes only. Okay. So I think, no, I don't remember the name. I think it's Mendeleev's cross. I don't remember the name of the biologist. So this is what they are saying, that the color of eyes follows this kind of pattern. Now what they say is, yeah, when to move. Okay, so from here the main question starts from here onwards. Above this, whatever is written, I have presented that information to you guys. So it says that the eldest child of a pair of brown-eyed parents. So you have two parents, right? So the parents have brown eyes. So both the parents have brown eyes and brown eyes, right? And it says that the eldest child have blue eyes. Okay, so the eldest children have blue eyes. So how is this possible? This is possible only if both the parents had XY, right? That is, they both had XY form of gene. Otherwise, this child would have either landed as XX or he would have landed as XY, which would have meant that he would have brown eyes. Okay. So the information that the child has blue eyes means both the parents have XY like pair of genes in them for eyes. Okay. So now the question is, what is the probability that exactly 2 of 4 children will have blue eyes? Okay. So we have been asked that 2 of 4 children will be blue eyes. Okay. So the first task would be to calculate the probability of a child being blue eyes. Okay. So probability of one child being blue eyes. Okay. So another thing is that whenever parents, so whenever a new offspring is born out of a parent, then the probability of transferring both the genes is equal. So the father can either transfer X or he can transfer Y with equal probability. Okay. So when will the parents have blue-eyed children? When both of them transfers X, right? This parent also transfers X, this parent also transfers X. So that is possible with probability half into half, because both of them are independent events, and the event of transferring X here is half, event of transferring X here is half. So the overall probability is 1 by 4. Okay. Now it becomes easy, right? So the probability of one child being blue eyes is 1 by 4. So probability of X is equal to 2 if we use this binomial distribution. This is nothing but 4C2, right? 1 by 4 to the power 2 into 3 by 4 to the power 2. Right. So this is 2 into 3, right, into 1 by 4 into 1 by 4, 9 by 16. And this is what we could get, 27 by this 2 and 2 cancel, 16 into 8, right? So, yeah, whatever is 16. So this is what we should get. Any doubts in this question or in binomial distribution as in whole? Okay, thank you. So now we go to some.
Excuse me, sir.
Yes, sir.
The blue eyes can occur. Just scroll up, please.
Yes.
Okay, sir. Okay. Sorry.
Okay. So I'll try to motivate why Poisson distributions are important. Okay. So what actually is the role of Poisson distribution? So these are used to approximate binomial distribution. First thing is that these are used to approximate binomial distribution. Okay. And that too happens in very special cases. Okay. When you have, so in binomial distribution, you had two things. One was your number of trials, that is your n. Another thing was your p, that is the probability of one particular trial being positive. Okay. So if your n is large and your p is small, okay, then with lambda is equal to np, your event follows Poisson distribution. Okay, so we'll look at an example. So the formula is very simple. It is given by your lambda to the power I. This is your parameter for your this distribution, Poisson distribution, lambda, and E is your exponential, nothing different here, e to the power minus lambda by I factorial. Okay, so here is an example that says, suppose that average number of accidents occurring weekly on a particular stretch of highway is equal to 3. Okay, calculate the probability that there is at least one accident this week. Now, if you look at this example via the lens of binomial distribution, you can, so of a particular car going through that stretch of a highway, you can divide it into two events, that either accident happens or accident do not happen. Okay, then you can see that the event of accident happening have very small probability. So your p is very small, right? Also, the number of cars that is passing through that particular stretch is very large. Okay, so we can use Poisson distribution over here with lambda equal to np. Okay, now in this question you will see that you don't have n available with you. Okay, so let's say you have a small stretch of road, then it is very difficult to count the number of car that is passing from there, right? Or also it is very difficult to estimate that what is the probability that a car will encounter accident. Okay, so when these estimations are pretty hard, but the other way around, that is your n into p. N into p gives you the total number of accident, right? So number of cars passing into the probability of a car meeting accident. So counting this quantity is much easier in this case. In those kind of scenarios, we use Poisson distribution. Okay, I hope I made my point clear. So in this question, we are given that the lambda or the NP value is 3. Okay, and we have been asked to calculate the probability that there is at least one accident this week. Okay, so we have to calculate that probability x is greater than equal to 1. Okay, this is again same as 1 minus probability that no accident happened, right? So this is lambda value is 3 into, sorry, 3 to the power 0 into e to the power minus 3 by 0 factorial, which is your 1. So this would be nothing but e to the power minus 3. Right. So this is when you use your Poisson distribution. Okay. So you got nothing but 1 minus e to the power minus 3. Okay. So now in the next question, we'll try to verify whatever I said, that you can estimate a binomial distribution via Poisson distribution, whether that is true or not. So the question says, suppose that the probability that an event, suppose that suppose the probability that an item produced by a certain machine will be defective is 0.1. Okay, so if so the p is 0.1. Find the probability that a 10 sample item will contain at most one defective item. Okay, so if x is the number of defective item, okay, then what we need to find is that probability that x is less than equal to 1, at most 1, less than equal to 1, which is nothing but probability x is equal to 0 plus probability x is equal to 1. Okay, and your p is given to be 0.1. N is 10, so this is 10c0, 0.1 to the power 0 and 0.9 to the power 10 plus NC1 0.1 to the power 1 into 0.9 to the power 9. Okay. So this is 0.9 to the power 10 plus 10 into 0.1, which is again 1 into 0.9 to the power 2. Right. So you get this equal to, I'm using a calculator over here. You can calculate it. I think you should get something as 0.7361. Okay. Now we will try to attempt the same question through Poisson distribution. Okay. So now what I said that for Poisson distribution, the lambda is equal to n into p. Although here the n and p are, your n is not very large and p is not very small, but you can estimate it. The estimate might not be very good, but you can still estimate it, right? So your n is 10 and your p is 0.1. So you get lambda is equal to 1. Okay. Now what you have to find that x is less than equal to 1, which is probability x is equal to 0 plus probability x is equal to 1, right? So this is nothing but lambda is 1, so nothing happens to it. So e to the power minus 1 by 0 factorial plus e to the power minus 1 by 1 factorial. I think this is what you should get. So this is nothing but 2 e to the power minus 1, which is approximately equal to 0.7358. So you can see that the approximation that we got is sort of close, right? It is 10 to the power minus 3 error. So still you can accept this also. Based on your application, either you can accept or not. Any doubt in Poisson distribution portion? We have one more question that I'll ask you guys to solve, but any doubt till now? Okay. So here is a question. So consider an experiment that consists of counting the number of alpha particles given off in a second by 1 gram of radioactive material. Okay. If we know from the past experience that on an average 3.2 such alpha particles are given. So here lambda is your 3.2. What is the good approximation to the probability that no more than 2 alpha particles will appear? Okay. So give it a try. I'll wait for 2-3 minutes and then I'll attempt this. So again, like I'll just murmur something. I'm not telling you the answer. But if you say like in any radioactive material, you will have very large number of atoms, right? And out of that atom, like if you have very large number of atoms, right? If 3.2 is the average number of alpha particles that is being emitted, so the probability of one particular atom like being like getting emitted would be 3.2 by n, right? So again your n is very large, and your probability is very small, right? So if you use your Poisson distribution, you will get a very good estimate. We shall possibly. Okay, so let's try solving this one. So now the lambda is given to be 3.2, right? And you need to find that your no more than 2 alpha particles is emitted. So probability that x is less than equal to 2, which is nothing but probability your x is 0, or probability your x is 1, or your probability that x is equal to 2. Okay. So lambda to the power 0, this is 1 into e to the power minus 3 by 3.2 by 1 0 factorial, that is 1, which is 3.2 into e to the power minus 3.2, again divided by 1. Now this particular term is 3.2 square into e to the power minus 3 by 2 divided by 2. Now this is just a calculation that e to the power minus 3.2 into 1 plus 3.2 plus this is 3.2 square by 2 would look like, let me calculate. So this comes out to be 2.56. Now I think we should get something higher. Wait. Yeah, sorry. I divided by 2. This is 5.12, right? Okay. So this is e to the power minus 3 by 0.2 into this is 239.32. Let's calculate, see what's e to the power minus 3.2. I'm using a calculator here. I'm not calculating those values. This is 0.0407 something. 0.0407 into 9.32, which is again 0.3799. Yeah, Rowan, you were correct. Hey, why I got 0.3799, Kushal? I think your earlier answer was correct. Did I make some calculation mistake?
Sir, I tried it 2 times on calculator and I got different answers. I think I need to check it again.
I got 3.7, this 0.3799. Yeah, so this is just a sort of calculation. Okay, so now let's move to something known as uniform random variable. So right till now, whatever random variables we covered, all of them were discrete random variables because they were taking discrete values. An event can occur 1 time, 2 times, 3 times. But now we have moved to the regime of uniform random variables. So what is uniform random variable? Let's say you have some portion. Okay. So let's say this is your portion. This is your A and this is your B. What uniform random variable says is that you have equal probability of getting any points between A and B. Okay. So so that so if the length of this line is B minus A, right? The length of this line would be B minus A. Then if you are equally likely to land on any point, then that equally likely probability is 1 upon B minus A. Okay, because the total probability is 1 and you need to divide it into the length of B to A. Okay, so this is how your uniform random variable is defined. Like if you are between A and B, then your probability is 1 upon B minus A. Otherwise, it's 0. So if you are outside this, the probability of any point outside this is 0. Okay. So you can also extend this to sort of two-dimensional thing. So if you have, let's say, a two-dimensional, yeah. So let's say this set is called S, and this is your point A2. This is, let's say, A1. Right. This don't assume this to be origin. Okay. And this height is, let's say, B1. This is B2. Then the area would be A2 minus A1 into B2 minus B1, right? And if you divide this by 1, you get the probability of any point. This is also a uniform random variable in 2 dimensions. Similarly, you can define for arbitrary dimensions. Okay. So where are these uniform random variables useful, and especially from our context of machine learning? Okay. So one place where I find the role of uniform random variable immense is to generate random numbers. Okay. So let's say you are working on some application, okay, where you need to uh, sort of mix some random noise, okay, some random noise. So for example, somebody interested in federated learning, okay, or where you want some stochasticity. So you want some random parameters in your model. At those kind of places, generating random numbers becomes very easy via this uniform distribution. Okay. So let's say I'll take an example of something known as symmetric label noise. And let's say you want to, yeah, let's take so I'm not sure how many of you are aware of this noise models. So let's say when we talk about training any machine learning algorithm, at least in supervised setup, what we say is that we have some X and we have some associated Y with it. Okay. So let's say, for example, so you have many classification tasks. You can take any example. For example, you want to classify a particular image belonging to a cat or a dog or any such examples. Okay. So generally what we assume is, so let's say we have some x1, x2 and so on, and we have some associated y1, y2 as our data set. Generally what we assume is that this y1, y2 that is available to us is always clean or pure. Okay. But actually this is not always the case. Okay. So sometimes it is possible that the person who is labeling the data points is not well versed with that area or not very good at labeling, but because he was available for a cheaper price to label, somebody hired him to label. Okay. Other possibility is that actually there are some images, let's say you want to classify, where we also don't know the person who is labeling, and he incorrectly classifies that point while creating the data point itself. Okay, data set itself. Another possibility can be that we are sort of lazy, we are working very late at night, mistakenly we did something. Another possibility can be somebody purposefully contaminated your data points. Okay, so then your data set becomes noisy. Okay, and now because your data set have noisy labels, what you want to do is you want to develop algorithms which works well with your noisy label data sets. Okay, so the example that I'm going to give you is related to a particular model of noise, okay, which is known as symmetric label noise. So what happens is, like, if you get some data from real life scenario, you don't know whether that data is noisy or clean, right? So if you want to develop an algorithm or test an algorithm that should work on noisy data set, how will you create a noisy data set? Okay, so this is not from sort of deployment purpose, but you should, when you are developing algorithms which should work on noisy data set, first you should know how to create any data or convert any data to be noisy data, right? So one way to do that is to induce symmetric label noise. Okay, so let's say you have some data points, these are your data points. Let's say these are 4 data points, and it has 2 labels, either it is 1 or 0. So what does symmetric label noise says? That with probability p, it will flip the label of any like any data point that you have. Okay, so if your existing data is, let's say, 1, then your modified data will be 0, or vice versa. With probability, let's say 0.5. Okay, so with 50% chance it will flip your data point. Now if you want to create such data where with 50% chance you flip this thing, then how can you create such data point? Okay, so the best way to do that is, so generating uniform values on your Python is very easy. You have a rand function in even math, you have random function in scikit-learn, you have it in PyTorch, you have it in NumPy. Every library you have random functions that you also uniform function. So what you can do is, let's say this is your number line, forget about this y-axis, and this is your 0, 1 interval, or you can take any length interval, right? So this is your 0 and 1. What you do is, for, let's say, for the first data point, you generated a uniform number, and the number turned out to be this point. Okay, you generated a uniform number between 0 to 1, and this is your 0.5 threshold. If the number that you generated, let's say this number generated is u1, if this u1 is greater than 0.5, then you don't flip. Okay, let's say for the second point, the number generated felt here. Okay, so if your u2 that is generated is less than equal to 0.5, then you change the label. Okay, so in this way, the new data set that you will get will have 50% noise in it. Okay, so yeah, so this is a very sort of vague kind of motivation for uniform random variable. It is useful in many other purposes also, but in machine learning, Generally, it is used to generate some random values or in related areas. Okay. Okay. So here is our first example. Yeah, somebody has something to say. No. Okay. So here is our first example. The example says that X is a uniformly distributed over 0 to 10 interval. Compute following probabilities. Okay. So f of x is given as 1 upon 10 minus 0 whenever your x is between 0 to 10. This is 0. What kind of using? This is 10 minus 0. Okay. This is nothing but 1 by 10. Right? And you want to find the probability that your x lies between 2 to 9. So what is the probability that your x lies between 2 to 9 is integration from 2 to 9, 1 by 10 dx. Or you can just see that if you have interval from 0 to 10, the length of this interval is 10, then what is the probability that it lies between 2 to 9? It would be the length of this portion, right? Length of this portion will be calculated via this particular integral. So this is nothing but your x by 10 in the range 2 to 9. This is 9 by 10 minus 2 by 10, that is your 7 by 10. Okay. Yeah. Now, B part says between 1 to 4, this is also same. You can just, this is x by 10, and you can just replace the values from 1 to 4. This is would be 3 by 10. C part says that your x is less than 5. So you would be integrating it from minus infinity to 5, 1 by 10 dx, right? But for, not 1 by 10 dx, but it would be f of x dx, right? F of x dx. The value of f of x for x less than 0 is 0. So this is equivalent to 0 from minus infinity to 0 dx plus, I could have solved this very straightforward, just looking at the interval, but I'm doing it purposely so that when you have some more complex probability distribution function, you will apply the same technique, that is integrating those things. Okay. So this is 1 by 10 from 0 to 5 dx. This term is 0 and this is 5 by 10, that is 1. Okay. Next is that your x is greater than 6. Okay. So your D part is x is greater than 6. So probability that your x is greater than 6 is nothing but integration from 6 to infinity f of x dx, which is nothing but 6 to 10, it would be 1 by 10 dx, and from 10 onwards it will be 0 dx. So this is nothing but 10 by 10 minus 6 by 10 plus 0, that is 4 by 10. Okay. Okay, so try this question. This is a very simple question on uniform distribution. I'll give you 4 minutes to solve. I'll start solving at 7:15. So I can draw a figure probably. Okay. So so starting from 7 a.m., let's say this is 7 a.m., the bus arrives at an interval of 15 minutes. So this is 7:15, this is 7:30, this is 7:45, and so on. Let's say this is 8, and so on. Okay. So if a passenger arrives uniformly between 7 and 7:30, so a passenger arrives uniformly between 7 a.m. to 7:30. This is our reason. Okay. So find the probability that he waits less than 5 minutes for a bus. Okay. So waiting less than 5 minutes would mean that he arrived in this particular area. So either he arrived between 7:10 to 7:15. That's when he would have waited less than 5 minutes. So this should be 7:10. Or he arrived between 7:25 to 7:30. Right? If he arrives in these two portions, then only he waits less than 5 minutes, right? So between 7 to 7:30, how many minutes are there? So there are 30 minutes. So if you look at the uniform distribution, this is given by 1/30. If your x is between 0 to 30, so this point get maps to 0, this point get maps to 30, okay, and 0 otherwise. So here are two sort of small windows of 5 minutes. So this is from 10 to 15, 1/30 dx, plus 25 to 30, 1/30 dx. So this is 5/30 plus 5/30. And this is nothing but here 1/3. So there is a 1/3 probability that the person waited for less than 5 minutes. Okay. Can you please attempt the second part at least now? That the person waits for at least 12 minutes. Okay, so this I'll verify. I haven't solved. We'll try solving. So others can also try. Then I'll start solving. I'll wait for one minute. Okay, 6 by 30, 9 by 30. Okay. So waiting at least 12 minutes means that he arrived at least 12 minutes before this portion, before this bus. So he should have arrived between this is 7:03, right? So he should have arrived in this window or here, right? Between 7:10 to 7:13. That's when he has to wait for at least 12 minutes, right? This portion or this portion. Okay. So this would be nothing but integration from 0 to 3 v by 30, sorry, 1 by 30 dx, and then it would be from 15 to 18. So this is yeah, oh sorry, not this portion, this is 7:10, sorry, this is my 7:15. So from here it should have waited 3 minutes, right? So this is 7:18. So from 15 to 18, 1 by 30 dx. This is nothing but 3 by 30 plus 2 by 30. This is 6 by 30 or 1 by 5. So this is something that was about uniform distribution. Any doubt till now? Okay. Now we move to a very important distribution.
Sir,
Yes. Yes.
this uniform distribution calculation,
Yes.
we can think of the CDF with the probability of 1 by n, whatever. Is it right? That's what we are doing, no?
We are thinking of.
CDF,
Mhm.
cumulative distribution function, with the probability function is 1 by n.
No, so actually not. We are thinking of this probability density function, not the CDF, but PDF of the function as 1 by n, where n is your length of interval, or yeah, but not the CDF.
But calculation, we are doing the CDF when we want the interval.
If you want to calculate the probability of this interval, then we will have bounds to be the endpoints of that interval. So you can also do via CDF, where you calculate CDF at this point minus CDF at this point. That is also a way. Was I clear?
Yes, it's clear.
Okay. Okay. So now we move on to a distribution known as normal distribution, or people also call it as Gaussian distribution. Okay. So this distribution is sort of very popular because of two reasons. First, so the reason is same, but I'll sort of talk about two applications. First is that if you have sufficient number of samples, which is generally people say if you have more than, let's say, 30 samples, okay, something more than 30, then the data points that you have collected sort of follows your normal distribution. Okay, so if you don't have any idea about your data points, then the best distribution you want to fit it to should be your normal distribution or the Gaussian distribution. So this looks something like this bell-shaped function, where this is your mean, okay, and then so you get many data points close to mean, and then you very not gradually but very sharply decline in terms of probability. Okay, so this is your mu. So when do we use it in machine learning or anything? So whenever you are not sure about distribution of anything, we model it via normal distribution. It is used at many places. Okay, so for example, so you are not sure your data points given some let's say label. Okay, so let's say you want to create a classifier. I'll just give you a brief overview. You want to create a classifier. You have data points with two labels. You can apply this even for more than two, but right now I'm just giving you for two. Okay, so let's say you have label 0 and 1. Okay, so you now if you model the probability of x given your y is equal to 0. So if you collect all the data points whose labels are y, and if you model this as your normal distribution function, okay, with so normal distribution function has two parameters. If you see, this is 1 upon under root of 2 pi sigma. Sigma is one parameter which later turns out to be its standard deviation, and another parameter is this mu, x minus mu square by 2 sigma square. So this mu is something that is mean. Okay, so if you model this by mu1 and sigma 1, then you can find some optimal values for your mu1 and sigma 1. Okay, for which this probability has sort of maximum likelihood or those kind of things. Similarly, you can model for y is equal to 1, you will get another best fit parameters, that is mu2 and sigma 2. Now, after you have learned your mu1 sigma 1 and mu2 sigma 1, sigma 2, if you have some new data point, let's say you get a new data point x and you want to find what's its y, then you can find its probability with respect to the first curve. You will get, let's say, some probability p1, and with respect to second one you get some probability p2. Then you can compare these two probability and tell which class this particular x belongs to. So if your p1 is greater than p2, that means you can assign class 0 to this particular. So this is one method of creating a classifier. At other places also, whenever you are modeling some kind of noise that is continuous in nature, you use a normal distribution. Okay, so yeah, so this is sort of a very useful distribution. So whenever you are not sure about any probability, what kind of distribution is being followed, you can go for normal or Gaussian distribution. Okay, so as I said, its formula is given by 1 upon under root 2 pi sigma e to the power 1 minus 1 by 2 x minus mu by sigma whole square. Okay, this 1 by 2 is outside the square. Okay, okay, so there is one more very small thing that I want to mention with respect to normal distribution. So if the value of mu is 1, sorry, if the value of mu is 0 and your standard deviation is 1, that kind of normal distribution is known as standard normal distribution. Anybody has anything to ask? I think somebody unmuted. Or anything to say? Okay. So if you have let's say a normal distribution following with mean mu and standard deviation sigma, you can convert this to standard normal distribution, okay, by just subtracting x minus mu and divided it by sigma. So for every random variable, if you subtract mu from it and if you divide it by sigma, you will get something that is your standard normal distribution. Okay. And why do we want to convert it to standard normal distribution? Because if you will see that calculation over here is not very straightforward. So it has exponential in it, -1, and other things involved in it. So when you have a sort of standard normal, first of all, the calculation becomes a bit easy. That is, this would become -1/2x square, right? And still, this is calculation can be difficult. So you have many standard normal tables available with you, which you can refer to solve your computation. Okay. So this was a small thing that I think there is a question related to standard normal distribution so normal distribution being converted to standard normal distribution. You just need to do this transformation x minus mu by sigma. Okay. Okay. So yeah, again, the standard normal distribution becomes very important in solving these kind of questions, and this kind of question you will encounter at many places. So let's say x is a random variable with mean mu and variance is equal to 60. So your standard deviation is 4. So you want to find probability of x is less than equal to 11. Okay. So the easiest way to do this is to convert this to standard normal distribution. So that would mean you want to subtract mean, that is x minus mu, mean is 3, divided by the sigma 4 is less than equal to, you will do it on both the side. Okay. So this is probability that now this has become a standard normal distribution. So this is z is less than, this is 2. And you can easily find out this value from standard normal table and replace it over here. Okay. So B part is probability that your x is greater than equal to -1. This is again, you can just replace that x is greater, sorry, x minus 3 by 4 is greater than -1 minus 3 by 4, or this would mean that probability of z is greater than equal to -1. So similarly, you can attempt other questions also. Okay. Any doubt till this point? Then we go to something known as exponential random variables.
Can you tell me the first one, no? Equal to probability of what is the less than? I am not that.
This one.
First one, the last column. Equal to what it is? Less than 2 something you wrote. Z you are writing.
Z
Okay.
Z is used to denote your standard normal distribution.
Oh, okay.
I
Okay.
forgot to mention. Yeah. Okay. So this exponential random variable might not be like very relevant to uh, machine learning directly. It can be used in some places, but it is very common and well studied in community who actually do sort of machine learning, because if somebody does a sort of advanced course in probability or even a basic course in stochastic processes, then he definitely encounters this random variable known as exponential random variable. So it is good to know about this random variable. So I'll motivate it by an example. Let's say you have a queue, right? So there is a very large, I would say, a different area of something known as queuing theory, where people do study the kind of problem that I'm going to say. So let's say you have a counter, okay, and you sort of know that people would come up in a queue. Let's say you are some bank, okay, and you know their average sort of how many customers you are expecting, or how much time at a gap of how much time the people would come. Okay. So exponential random variable gives you the probability of gap between two customers. So let's say you have your first customer has arrived and you want to estimate what is the time after which the second customer will come. So exponential random variable gives you an estimate of time after which your second customer would come. So based on that, you can decide on how many counters you want to open for cash deposit, how many counters you want to dedicate to something. People even use it in medical field. So how to queue your patients, right? So like how many operation theaters you want to open in a hospital so that the patients don't suffer, and those kind of problems are also tackled. So this is a random variable which gives you the amount. So this x represents the amount of time until the next event occurs. Okay, so this is given by lambda e to the power minus lambda x. Okay, whenever your x is greater than equal to 0, obviously the time would be in positive. Okay, I'll come back to the memoryless property. Okay, but let's first look at what it is meant by lambda. Okay, so if you look at over here, lambda is the reciprocal of your mean, right? Okay, so yeah, so lambda is so if you go in more deep in Poisson process, these things will be slightly more clearer to you. But for right now, you know that your lambda is the reciprocal of your mean. Okay, so let's solve an example first. Then we will go to what is memoryless property and tell you what it is. So it is saying that suppose that the number of a mile that a car can run on a battery wave is exponentially distributed with an average of 10,000 miles. Okay, so your mean is given to be 10,000 miles. So after 10,000 miles, that is the time your battery will die or you will have to replace the battery. Okay, so it is asking that if a person desires, so here your lambda value would be 1 by 10,000, right? So if a person desires to take a 5,000 mile trip, what is the probability that she will be able to complete her trip without having to replace her battery? Okay, so we have been asked that probability of x is greater than equal to 5,000. Okay, so this is nothing. Here are two formulas that we will sort of use for this. So based on this, people have integrated it like what is probability of x is less than x. This is nothing but integration from 0 to x lambda e to the power minus lambda x. Okay, and if you integrate it, you will get this value. Okay, okay, so if probability of x is less than equal to x is given by 1 minus e to the power minus lambda x, then what is probability of x is greater than equal to x? This is just 1 minus probability of x is less than equal to x, which is nothing but e to the power minus lambda x. Okay, so probability of x is greater than equal to 5,000 is nothing but e to the power minus, now lambda is 1 upon 10,000 into 5,000. So we'll just cancel these things. So this is e to the power minus half that you will get. Okay. Now coming back to what is known as memoryless property. So memoryless property says that how should I quote it? Okay. So the probability of an event happening after, let's say, what does this mean? Let's say when we began this lecture, so what is the probability that the internet would stop working from my side after, let's say, 10 minutes. So X is the event that internet would stop working. Internet would stop working after 10 minutes. Okay. So this is how we represent this probability. Now, what memoryless property says is that this should be equal to, let's say, now we have finished around 1.5 hours in this lecture. So given that we have already completed that our X is already greater than 90, what is the probability that it will now again stop working after 10 minutes from now? Okay. So this is 90 plus 10. So memoryless property says that these two probability must be same. That in so like even after we have finished sort of 90 minutes, the probability of internet getting affected is same as when we began our process. Okay. So this is what is known as memoryless property, and your exponential random variable is the only continuous random variable satisfying this property. Okay. So this is how this is written, that probability that your X is greater than S plus T is same given that your X is already greater than T, it's same as probability that your X is greater than S. Okay. I think I have one more question on this. No, sorry, I should have included one more question. Okay. Any doubt till this point? Then we'll go to something known as joint distribution. I think I should have some. Okay. So till now, I'm really sorry. So whatever examples we did were related to one random variable, and we were assigning some probability function on top of that random variable. For discrete case, that was our PMF. For continuous case, that was our PDF. Right. Now, events can occur in sort of combinations, right? So you can have two random variables which you represent as a sort of random vectors, or you can have even more than that. You want to represent their joint distribution. Okay, joint distribution means that if your X is equal to Xi and your Y is equal to Yi, so this terms gives you the probability that your X is equal to Xi and your Y is equal to Yi. Okay, so this is something known as joint distribution. There is another term that is associated with this thing. Okay, so before going to example, let's look at what is known as marginal distribution, which is related to joint distribution. So this gives you, so this f of x is equal to xi, comma y is equal to yi, gives you the distribution of x being xi and y being yi. Let's say I take summation or integration, whatever is possible, if it is discrete or continuous based on it, with respect to one of the variables. Okay, so let's say I take its sum, or integration is just sum, right, in continuous case. If I take its sum over all yi's, what do I obtain? I obtain x is equal to xi. So I get now distribution in just one variable, which is what is the probability that my x is equal to xi, because I summed over all the yi combinations. Okay, so these distributions are known as marginal distributions. If you would have summed up with respect to xi, you would have got marginal distribution for y. Okay, so let's do an example and we'll see later on how the marginals look. Okay. Okay, so the question says, suppose that 3 batteries are randomly chosen from a group of 3 new, 4 used but still working, and 5 defective batteries. Okay, there are 3 batteries that we have chosen. Now let X and Y denote respectively the number of new and the used but working batteries. So X denotes number of new batteries in the 3 batteries that we have randomly chosen, and Y denotes number of used but working batteries. Okay. Okay. So we have been asked to find its joint mass function, that is Pij, when your X is equal to I and Y is equal to. Okay. So now you have 3 batteries. So let's try to draw a table of this for this PMF. So I'm really yeah. So if this is my X and this is my Y. So X can take value 0, 1, 2, 3 because we are drawing 3 batteries, and Y can also take 3 values, that is 0, 1, 2, 3, right? So we are drawing 3 batteries from group of 3, right? So now we have to calculate the probability that my X is 0 and Y is also 0. Okay, so this place we want to fill in. Okay. So if my X is 0 and Y is 0, what does that mean? That all the 3 batteries has been chosen from 5 defective batteries. So there are 5C3 ways of doing it, divided by the total number of ways. So this is 3, 4, 7, 5, 12C3. Oh, no, sorry. Yes, I think we can straight away go for probabilities. Just give me a second. Uh, give me a second, please. Yes, I think I have done this correctly. Yeah. So this will be the probability that needs to be filled here. That is 5C3, right, divided by 12C3. Now, for this case, when you have X is equal to 1, so that means you have to choose 1 from the 3. So this is 3, 1. And rest 2 you have to choose from the defective ones. So 5, 2, again divided by 12C3. So this way you can fill up this table. Okay. So,
Sir, I think Y will go up to 4.
but we are choosing only 3 batteries, right? So if you are picking only 3 batteries, how can your Y be 4? How can your out of 3, how can you get 4 used batteries? That is not possible.
That is not possible. Okay, sir.
So yeah, so let's look at a continuous example. So in this case, you are already given with the density function, that is 2 e to the power minus x e to the power minus 2y. Okay, defined over this particular support. So I just used a term called support. So for a distribution or a random variable, okay. So what is support? Support for a distribution is any value of x. So if it is a random variable in one variable, then it is the value of x for which your f of x is strictly greater than 0. That is, it is non-zero probabilities you are getting. Okay. So if it is a multivariate random variable, then it would be the set or the combination or the pair of values on which your f of x is greater than 0. So if you look here, when your x and y lies in intersection of these two region, then you have non-zero values. That's why this is called as support of some random variable. Okay. So first part is to calculate probability that your x is greater than 1 and y is less than 1. Okay, this is simple, right? So you want to calculate integration of this. So this would be double integration now. Earlier we had summation with respect to just one variable. Now we have two variables, so we'll have two integrations. So your y value is from 0 to 1. I'm just ignoring the case when y is from minus infinity to 0, because that would be just 0 and writing that is unnecessary. And this is from 1 to infinity. And then you integrate e to the power minus x, e to the power minus 2y, dy dx. So when you, I'll just try to solve one part because I have forgot integration. It has been a long time when I did it. So this is 1 to infinity. This would be, I think, this should be minus 1 by 2. Am I doing it correctly or I'm making some mistake? E to the power minus x, e to the power minus 2. Is this the integration that we'll get with respect to y? So whoever is doing this BTech can probably help me here. Is this integration correct?
Yes, sir.
Okay. So we can put the values now. So this is from 0 to 1. So we'll get 1 to infinity. This is minus e to the power minus x. If we put 1 over here, we get e to the power minus 2, and then we get minus 1, right? Now this is dx. So we can take the this term outside. So this is e to the power minus 2 minus 1, and for this we will have one more minus over here. So this would be e to the power minus x from 1 to infinity. This is yeah, power minus 2 minus 1 and 2 minus 1. That is your 1 minus e to the power minus 2. I think this should be correct answer. And yeah, there is one more. This is e to the power minus 1 also, right? Yeah. So this way you can approach. So for the rest, I won't integrate, but I'll write how. So this is B part is probability that your x is less than y. This is nothing but your x is now limited upper bounded by y. So your integration would run from 0 to y for x variable, and your y variable is free, so this should be 0 to infinity. And now this is 2 e to the power minus x e to the power minus 2y. Now this time you are integrating first with respect to x because you have written the limits of x first, then with respect to y. Okay. For C part, it is probability that your x is less than a. So this is your, so y would be 0 to infinity, your x would be from 0 to a. Now again 2 to the power minus ex e to the power minus 2y dx first, and then your dy. And one more thing, so just to mention that in this only, as this is f of xy, if you would have integrated it with respect to just let's say this is 0 to infinity, you integrated this with respect to, let's say, dx, you would have got f of y of y. That is your random variable for y variable. Okay. So probability distribution function for your random variable y. Okay. Similarly, if you integrate with respect to y, you get marginals with respect to your x function. Okay. Okay. So now there are two terms. Uh,
Sir,
yes.
is it called marginal distribution there also when you do partial integration with that? Just now
Uh,
previously you done.
where this one, na?
Yeah. Same,
This
same,
is
same.
known as a marginal distribution. This particular term is your marginal distribution.
Clear. Thank you.
Okay. So we have two more terms left for today. One is called covariance, and another is known as correlation. So these terms sort of so we have sort of seen covariance matrix earlier also, but now like this is sort of a repeat thing, but we'll do. So covariance between two random variables is sort of gives you how much are they are independent of each other or related to each other. So when you have your feature vectors, at that time you need to calculate covariance and correlation to check whether some features are reductant and you want to just remove that feature and then train your model. Okay, so at those kind of things this becomes useful. So covariance of x and y is given by expectation of xy minus expectation of x into expectation of y, and correlation is just your sort of I won't call it normalized, but yeah, this is divided by under root of variance of x into variance of y. We'll just look at a simple example. Okay, so we are given with two distribution, a joint distribution of x and y. Okay, and we want to find covariance of xy, and then this symbol is for correlation between x and y. So what is formula for covariance of xy? This is expectation of xy minus expectation of x into expectation of y. So to calculate expectation of xy, we have every information available over here. But in order to calculate the expectation of x and expectation of y, we will need marginal distribution for x and marginal distribution for y. So we will calculate that also over here. Okay. So first of all, let's calculate what is expectation of xy. So this is nothing but summation over x and y. This is p of x comma y into your xy, right? So let's take this sum. When your x is 0 and y is 0, probability is 1 by 8, but this is 0 into 1 by 8. Again, when your x is 0, everything would become 0 only. So I am ignoring this row. Okay. And for this column also, there is no need to write it down. So I'm just writing, ignoring this row and this column. Okay. So now this would be plus 1 into 1 into 1 by 8 plus 1 into 2 into 2 by 8 plus 1 into 3 into 1 by 8. Okay. So this is nothing but 1 by 8 plus 4 by 8 plus 3 by 8. This turns out to be 1. Okay, let me verify this whether this is actually correct or not. I think this should be correct, but let me just cross check because we don't want to make a mistake in first step of our question. Yeah, this is 1. Okay. Now, in order to calculate the this expectation of x and expectation of y, we need marginal distributions, right? So from the table, okay, so what is uh, probability of x is equal to 0? So I said you just need to sum over y. Okay, so probability of x is equal to 0 and y is equal to yi. You need to sum over all the yi. So when your x is 0 and y is 0, so this will have 4 terms, that is 1 by 8 when your x is 0 and y is 0, plus when your x is 0 and y is 1, this is 2 by 8 plus 1 by 8 plus 0, right? This is 4 by 8 or half. So in the table you can see this is the sum of this row. right? And this one would also be half. So the probability distribution for this marginal distribution for x looks like x can take two values, 0 and 1, with probability half and half. Okay. So what is expectation of x? Expectation of x is 0 into half plus 1 into half, that is half, right? So now if you want to find probability distribution for y, you can just do it by taking the sum along the column. So because when your y is fixed, so you can vary the x, so you will get the sum along the column. So this is 1 by 8, this is 3 by 8, this is 3 by 8, and this is 1 by 8. So you can write y takes 4 values, 0, 1, 2, 3, with probabilities 1 by 8, 3 by 8, 3 by 8, 1 by 8. Right, so this is 1 by 8, 3 by 8, 3 by 8, and 1 by 8. And then what is expectation of y? Expectation of y looks like 0 into 1 by 8 is 0. So this is 3 by 8 plus 6 by 8 plus 3 by 8, right? So the value that we get is 12 by 8, right? Which is your 3 by 2, right? So now what is your covariance between x and y? This is expectation of xy, that is 1, minus expectation of x into expectation of y, which is your 3 by 2. So 1 minus 3 by 4 is nothing but 1 by 4. Okay. Now, in order to get correlation between x and y, okay, so I can use a better symbol. I should use the one here. Yeah. So this is covariance of xy divided by square root of variance of x into variance of y. So let's calculate variance of x and variance of y. So here, what is variance of x or sigma square? This is expectation of x square minus expectation x whole square, right? So from here we can calculate what is expectation of x square. This is 0 would be 0 plus 1 square into 1 by 2 is 1 only. So 1 by 2 here, right? So this is 1 by 2. So we will get 1 by 2 minus 1 by 2 square, that is 1 by 4. This is nothing but 1 by 4, right? And now what is variance for this y with random variable? This is now what is expectation of x square? This is 0 plus 1 into 3 by 8 plus 4 into 3 by 8 plus 9 into 3 by 8, right? So this is 3 plus 12 plus 27 by 8. So this is 3 to 5, 7 to 1, 3 plus 1. So this should be this only. Okay. I think I made correct calculation, right? Okay. If there is some calculation mistake, I request you to please sort of check. Okay. So what is my now variance of x? Sorry, variance of y. This is 42 by 8 minus 9 by 4, which is 84 minus 9 by, sorry, this is 42 minus 18 by 8, which is 4 then Boolean. Yeah. This is what we get. Yeah. Okay. So yeah. So what is my covariance? This is 1 by 4 divided by square root of 3 into 1 by 4, right? So this is 1 by 4 divided by square root of 3 by 2. This is 1 by 2 divided by square root of 3. Sorry, yeah, this is correct. So 1 by 4 into, I think I have made some calculation mistake there, but this is what you would get. This is how you should apply. So this is what I had prepared for today. If you guys have any questions related to what I covered today, you can please ask. Next week that would be the last lecture, and I'll be covering SVM. So yeah, so theoretically I'll be dealing with SVM. So if nobody
Sir,
Nobody has it. Yes.
sir, can you tell about the source of these questions which you take
sure,
today for class?
I
Sure.
mentioned the
I
book.
mentioned
I'll include the
I'll
cover also.
Okay,
include also.
so these questions are from that same book.
I did the example
I
Okay,
question.
Sheldon
did the
Ambrose.
example.
Yeah. So there are two,
So
three
there
books
are
by Sheldon Ambrose. I will try to attach the cover page. Just give me a second if this gets copied. Yeah. So this is the cover. Introduction to Probability and Statistics for Engineers and Scientists. So this has the level of questions that is required for this course or basic understanding. This is a good book. You can even read theory from here, and there are quite a good number of questions. Some questions I randomly take from internet, which I didn't found in this book. I took from other sources also, but this is the more or less the book that I followed for this.